All right, howdy. So today I'm going to talk about circuit elements here, circuit elements, and what those are batteries, capacitors, and resistors. And later on we'll talk about another one, a fourth one called an inductor, but that requires a little bit of magnetism. So we're going to stick with the electrostatic kinds, right, or the quasi-electrostatic kind of things. So we're just going to talk about batteries as power sources, capacitors to store charge, and resistors to dissipate the charge, or to move charge around through. That's what a resistor is going to do. It's going to move charge from one place to another. So the first thing, like I said, is going to be the battery. And I'll give you lots of different things to talk about. We talk about circuit analysis in the next two of these lectures. The battery, which we're going to draw like this. Okay, it's a circuit element, so this is the negative terminal. This is the positive terminal. So when you look at a battery, this long bit, rather than the short bit, is always going to be the positive side. That's the positive side of your battery. And your battery is going to give a little bit of electromotive force, like we talked about last time, delta V, which means that the voltage on this side is going to be less than the voltage on this side. Okay, so a battery cell, a single cell, we talked a lot about batteries already, increases the potential. From the negative to the positive terminal. I don't want to use too many lines because I'm not learning. Here's me right for talking. All right, so that just is what I said over here. When we go over that battery in a circuit, that's what's going to happen to it. Now, we've probably talked a little bit about this already, but we're going to talk about series and parallel for each one of these ideas. Okay. So A in series what's going to happen is they're going to work in sequence. So if we were to do V0 here, put a battery, two batteries in series, one right after another, like this, we can put the terminal there. This is equivalent. They're both have different voltages. 2 going to V0 plus going to at the positive end of this series, V0 plus delta V1 plus delta V2. Okay. So in series they just act together to increase the potential. In parallel, by contrast, which you've already talked about, it's only one R in parallel. 2 L's, actually 3 L's, but the last one doesn't count. What's going to happen is they're going to act longer. Okay. So when we do this, the two batteries, 1 and 2, this is V0, and this is delta V, and these are both the same because these are ideal wires. For real wires, you can have real wires connecting two batteries with different voltages, but you can't do the same thing for ideal wires. It has to be a real wire to do that. So there technically has to be a resistor in between them somewhere in a real system. These still raise you up to the same amount of potential, which we already talked about, right? So the thing that this does, it allows you to act longer. So every battery has a lifetime in amp hours. So if this guy has 100 amp hours and this guy has 100 amp hours, it'll last 200 amp hours. That's how much energy it can provide. But but they don't add any more potential. So you give it the same amount of energy. You can give more things the same amount of energy with B. We give the same thing more energy with A. So same thing, more energy in series. More things, the same energy in parallel. Maybe that makes sense, maybe that doesn't. Hopefully it does. So you can power twice as many light bulbs for the same amount of time if you have two batteries in parallel, for example. Like I said, C batteries, yeah, but let's not call that C. But like I just said, the batteries need to be the same. So if we have these two batteries in parallel, they need to be the same if they're connected by an ideal wire. Because technically everything on that ideal wire is the same potential, right? So if you go from V0 to two different potentials here, you get a current flow from one to the other, as we already talked about with Ohm's law. If that's going to happen, there should be a resistor in there. And C will just be the ground, which is a bonus fourth circuit element. Those place the voltage to 0, or the potential to 0. And basically what a ground would look like would be something like this. If I were to take this out here, I would take a ground out there, and I have these three lines, almost a triangular pattern. They get smaller as they come down. So these three lines indicate a ground, and that says the voltage is equal to 0, which means V is equal to 0 along this entire point here, which means that after you go up that delta V, you just go to a potential of delta V up here. All right. This is just telling us where 0 is, basically. It has real consequences in a real circuit, right? You don't want a floating ground for a lot of applications because sometimes different parts of your circuit will end up at different potentials than you wanted them to. So putting grounds in strategic locations, if that's what you're going to do, is design circuits, which probably you aren't for this class, is important to make sure that places where you think there's a certain amount of potential, there is that potential. All right. And obviously you can screw things up pretty badly there. So that is what happens with circuit elements. I'll do one example that will use both series and parallel. I think maybe, let me check. Yeah, each of these examples is going to include both series and parallel in them for this lecture. So hopefully that will give you a little bit more idea about what's going on in each one and how to analyze stuff sort of that way. In the next lecture, we'll talk about real circuit analysis, and we'll talk about Kirchhoff's laws and things like that, and how to analyze circuits. Here we're just talking about basically what happens when you have a bunch of the same thing in a fairly simple system. Right? We'll talk about more complicated things in lecture 7, and then we'll talk about RC circuits in lecture 8. But next, I want to talk about capacitors. All right?